Hi, everyone. Good morning, good evening, good afternoon. Wherever you are from, thank you so much for making the time today to join us. My name is Keen Chen. I'm with the marketing team at VeloDB and Apache Doris. So we know a lot of you came today to learn more about Apache Doris 3.1, and it is an important release. So today, Vincent Zhang, Apache Doris PMC, will walk you through all the major upgrades and updates in this release. The two main updates are better JSON analytics for observability workloads, and also better Lakehouse capability, more specifically, a more complete integration with Iceberg and Paimon. Vincent will have a lot more on all of these. And just a quick housekeeping notes. After Vincent's presentation, we'll have a live Q&A session. And you should be able to see a Q&A tab at the bottom of your screen. So feel free to type in your question anytime during the presentation. We'll address them at the end. So with that being said, I'm going to turn the mic to Vincent. So Vincent, all yours.
Oh, thank you. Hello everyone, I'm Vincent, a PMC member of Apache Doris, and I'm the release manager of version 3.1 in the community. Today I will be presenting an overview of the Doris 3.1 release. Today's presentation will cover the following sections. First, I will give you a quick overview of the overall state of Doris 3.1. Second, I will dive into the key highlights and the new features included in version 3.1. Third, I will outline the behavior changes introduced in this release. Finally, I will answer your question. First, let me introduce the goals of Doris 3.1 release. Doris 3.1 is built upon Doris 3.0.6. The 3.0 series has reached a highly stable status by version 3.0.6, providing an excellent foundation for the 3.1 release. Previously, if you needed the share nothing deployment, we would recommend version 2.1. If you required a decoupled storage and compute deployment, we would recommend version 3.0. With the release of 3.1, we now recommend using version 3.1 regardless of your deployment model. As you can see, community deployment activity remains very strong. Despite being positioned as a minor version iteration, more than 100 developers have participated in this development, contributing their efforts. There were over 800 commits in total, including more than 100 new features, as well as over 200 optimizations. Now let's take a quick look at the key highlights of the 3.1 release. As you know, observability is an important capability for Doris, and using Doris for observability analytics is becoming increasingly popular. Analyzing logs, user behavior, and LOT telemetry data are among the core use cases that Doris targets. For this scenario, the Doris community has received extensive feedback and requests from users. In response, Doris 3.1 has made significant improvements to the variant data type and indexing capabilities to better serve these workloads. Another major trend in the big data is Lakehouse. Currently, Iceberg and Paimon have become the de facto standard data formats in modern data platform architectures. They are decoupled with query engines, friendly with object storage, and they have rich data management features with acceptable query performance. So they are widely used. Starting with version 3.1, Doris treats Iceberg and Paimon as first-class citizens, equal in importance to native Doris tables, and is committed to delivering comprehensive querying and management capabilities for Iceberg and Paimon with the Doris ecosystem. These two areas represent the most significant updates in the 3.1 release. In this live session, I would provide a high-level overview of the features and use cases for both. In the following up 3.1 new features webinar series, we will host dedicated sessions for each of these topics, diving deeper into usage patterns, best practice, and internal implementation details. In addition to these two major areas, the 3.1 release also includes enhancements related to data ingestion and query performance, which I will cover in this presentation as well. All right, next I will introduce the key new features added in version 3.1. First, let's talk about observability. In version 3.1, we have significantly enhanced the capabilities of the warrant data type. Let me first introduce the characteristics and the use cases of the warrant type. The warrant type, similar to the JSON type, is designed for semi-structured data scenarios. Compared to JSON, warrant stores its internal subcolumns separately, which results in better query performance and more efficient storage utilization. At the same time, JSON formatted data can be directly ingested into a warrant column without any modification, simplifying the data ingestion process and eliminating the need for additional pre-processing. Warrant type is also like the structure type. Warrant supports nested and complex data structures, making it suitable for storing user profile tags, order details, and similar data. Moreover, compared to the struct type, warrant doesn't require predefined subcolumn schemas, offering greater flexibility. This makes it ideal for storing data from different sources with different formats, slowing changing data or data subject to frequent schema changes due to the evolving business requirements. Therefore, the warrant type is particularly well suited to observability use cases, such as IoT, marketing automation, advertising, event tracking, security auditing, and logging. However, the current implementation of warrant type in Doris still faces several practical challenges. The first one is subcolumn explosion. As the number of internal columns growing significantly, it leads to increased storage overhead and degraded query performance. The second one is lack of strong schema enforcement. Without strict schema constraints, it's easier for dirty data or type mismatch to occur. The third one is limited fine-grained optimization. It's not possible to create indexes on subcolumns or apply other detailed optimization. To address these issues, Doris 3.1 introduced two highly useful new features for the warrant type, sparse columns and schema templates. With these enhancements, the warrant type achieves even greater flexibility. With sparse column support, the number of subcolumns that can be handled scale up to 10 of thousands. With schema templates, you can achieve finer grained control over subcolumn behaviors, enabling more targeted data ingestion and query. In terms of cost efficiency, with sparse columns, metadata and index storage overhead are significantly reduced. Through vertical compaction of subcolumns, column-wise grouping and merging can be performed independently, resulting in lower memory consumption. With the schema template capabilities, index can be configured individually for specific subcolumns, avoiding unnecessary indexing overhead. The newly introduced schema template capability for the warrant type brings the following significant benefits. The first one is the type accessibility. In previous versions, the data types of warrant subcolumns were inferred during data ingestion, In version 3.1, you can now specify the data type for each subcolumn. This ensures more stable query results, avoiding unnecessary query errors, index invalidation, and performance overhead. The second one is faster and more accurate retrieval. With schema templates, different indexing strategies can be specified for individual subcolumns, significantly improving query efficiency and reducing query latency. The third one is fine-grained index cost control. Instead of inheriting indexes uniformly across the entire column, indexes can now be configured preciously for subcolumn. This approach dramatically reduces the number of indexes, rate amplification, and storage costs. The fourth is improved maintainability. A schema template effectively adds data contracts to JSON data with type and index definitions. The schema become more observable, making it easier to resolve issues. The last one is evolution-friendly design. High-frequency access subcolumns can be templated and optionally indexed, while long-tail or infrequently accessed fields retain full flexibility for dynamic expansion, achieving optimal performance without losing extensibility. Next, I will introduce the improvements of inverted index. Using inverted indexes, users are primarily concerned about query performance, recall rate, and storage costs. Doris 3.1 introduces a completely new inverted index format, inverted index format of version 3. The version 3 inverted index format significantly optimizes storage space usage, further reducing the storage cost of using inverted index. Compared to the version 2, the version 3 introduced two key features, CSTD direct dictionary compression and position-based compression. Leveraging these two newly introduced compression techniques, version 3 index files are much smaller, reducing I/O overhead. As demonstrated by test results on the HTTP logs and the Logsbench datasets, using the version 3 format can reduce the storage space by up to 20%, making it ideal for large-scale text data and log analysis scenario. As mentioned earlier, the three key concerns users have when using inverted index are query performance, recall rate, and storage cost. To improve query recall, Doris 3.1 introduces three new tokenizers and now allow users to define custom tokenizers. The first new tokenizer is the ICU tokenizer, which provides excellent support for internationalized text and adapts well to multiple languages. It is recommended when high precision tokenization is required. The second one is the IK tokenizer, a widely used Chinese tokenizer in Elasticsearch. Doris has introduced this tokenizer to enhance the accuracy of Chinese text segmentation. For workloads primarily involving Chinese language data, this tokenizer is strongly recommended. The third tokenizer is the basic tokenizer. It provides only fundamental tokenization capabilities, such as splitting text by white space. As a result, it offers the fastest tokenization speed and is suitable for scenarios where high segmentation accuracy is not required, helping to boost the overall performance. If none of the above tokenizers meet specific requirements, users can also use the custom tokenizer. The customer tokenizer allows users to define tokenization logic according to their unique needs, further improving text retrieval recall. Users can custom tokenizer based on their particular use cases, precisely controlling how text is segmented into tokens. This is all of the overview of the observability enhancements. We will cover this topic in great detail in the dedicated live session. Stay tuned for our upcoming announcements if you are interested in this area. Now let's move on the Lakehouse direction. As mentioned at the beginning, Iceberg and Paimon are becoming increasingly popular in data platforms and have evolved into fundamental components, effectively becoming the de facto standard storage formats for data lakes. Doris is embracing this trend by treating Iceberg and Paimon as first-class citizens, continuously integrating their features and optimizing query performance on them. Let's first look at the functional enhancements. Doris 3.1 introduced support for the following Iceberg and Paimon capabilities. First one is branch and tag functionality. Both Iceberg and Paimon offer Git-like capabilities for branches and tags, enabling fast, lightweight access to historical data and the creation of data copies. This is particularly useful in data science and AI training workflows. Doris 3.1 supports all branch tag operations for Iceberg, including querying, creating, and deleting, as well as querying operations for branch and tags in Paimon. The second one is system tables, a highly practical feature that allows users to inspect metadata about tables. Doris 3.1 supports querying all system tables of both Iceberg and Paimon. Third, Doris 3.1 now supports querying Iceberg's views and Paimon's incremental data between two snapshots. Finally, Doris 3.1 natively supports using outer statements to modify the schema of Iceberg tables. This enables one-stop unified management of Iceberg tables directly within Doris, eliminating the need to rely on external tools like Spark. After covering the functional improvements, let me now introduce the performance enhancements for data lake queries. In Doris 3.1, two key features have been introduced to significantly improve data lake query performance. The first one is dynamic partition pruning, and the second one is batch shard execution. In data lake queries, opening files is an expensive operation. Therefore, partition pruning can greatly enhance query performance. Previously, Doris only supported the static partition pruning, which means pruning would only be applied when there were partition-level filter conditions on the table. In Doris 3.1, dynamic partition pruning is now supported in multi-table join scenarios. Partition column predicates are generated based on the data from the right side table, enabling real-time partition pruning on the left side table. This significantly reduces data I/O. In typical benchmark test scenarios, the feature improves query performance by over 40%. Another costly operation in data lake queries is shard generation, which requires scanning and collecting metadata from all files in a table. Due to the potentially massive number of files, this process can consume substantial memory on the front end of Doris. To address this, Doris 3.1 introduces batched shard execution, which generates query shards in batches and allows shard generation to proceed concurrently with actual query execution. This not only speed up query processing, but also significantly reduce memory usage on the front end. Doris 3.1 not only enriches the data lake query capabilities and improves query performance, but also provides user-friendly connector interfaces for catalogs. First, it aids support for the Iceberg REST catalog. Version 3.1 further enhanced the support for the Iceberg REST catalog by supporting multiple backend implementations, including Unity, Polaris, Gravitino, and Glue, and introduce support for vendor credentials, enabling more secure and flexible management of SaaS credentials. Second is also added support for the Paimon REST catalog. Version 3.1 supports the Paimon REST catalog based on Alibaba Cloud DLF, allowing direct access to Paimon table data management by newer version of DLF. Finally, it introduced support for multiple Kerberos authentication environments and multiple Hadoop cluster. Version 3.1 allows users to configure distinct Kerberos authentication and Hadoop cluster settings for different catalogs, enabling Apache Doris to perform unified querying across data sources with diverse configurations in complex environments. The final major enhancement for Lakehouse in Doris 3.1 is deep integration with async materialized views. Since the async materialized view introduced in Doris 2.1, async materialized views have received significant attention and widespread adoption. They are primarily used in two key scenarios: lightweight ETL and query acceleration. Partition level incremental refresh and partition level transparent query rewrite are the core capabilities that enable these two use cases. Incremental refresh provides more efficient data processing, while transparent rewrite ensures constant query acceleration even the base table data changes. Previously, these two features were fully supported only for native Doris tables and Hive tables. In Doris 3.1, Iceberg and Paimon are now treated as the first-class citizens. These two critical capabilities have been extended to Iceberg and Paimon tables as well. With this enhancement, Doris 3.1 enables new usage pattern on Iceberg and Paimon tables, such as accelerating hot queries and automatically hot code data tiering. Here we demonstrate the effect of accelerating queries using async materialized views on Iceberg. On the left side is the hot code data tiering. The hot data from the table is automatically ingested in Doris via an async materialized view without modifying the queries. Doris automatically routed the queries to the hot data, achieving over 3 times the performance improvement. On the right is the simulation of targeted query acceleration. By creating async materialized view for specific queries, even greater performance gains can be achieved. The maximum improvement shown in the right chart reached up to 7 times. The above covers the new features in the Lakehouse direction. As mentioned, we will also host a dedicated next session later to provide a more detailed introduction to the usage and underlying implementation of these features. We welcome everyone to follow and attend our upcoming live stream. Next, I will introduce other notable updates in Doris 3.1. The first is flexible partition column updates for merge on write tables. Doris previously provides partition column update capability for merge on write table. However, earlier version required that all rows in a single import batch updates the exact same set of columns. In certain scenarios, records eliminated by source systems typically contains only the primary key and the columns that have been changed, meaning different rows may update different columns. To address this requirement, Doris has introduced flexible column updates. This feature significantly simplifies the user-side effort of batching data by column and improve write performance. To use this feature, when create table, you need to add an additional property and enable unique key skip bitmap column. Then, when importing data via stream load, specify the update module as update flexible columns. This allows data to be imported in the format similar to what is shown in the right-hand diagram, where each row can update different columns. Next, I will introduce performance improvement in Doris 3.1. First, enhancement of partition pruning. Partition pruning is a critical technique for improving query performance. On tables with a large number of partitions, evaluating each partition could be pruning or not can be time-consuming. In version 3.1, this frequently used scenario has been specifically optimized. When columns with date or datetime type are used as partitioning columns, partition pruning has been upgraded from linear search to binary search. Additionally, hotspots in the code path have been fully optimized end-to-end, resulting in over 20 times performance improvement. Also, Doris 3.1 now handles more types of partition pruning. In real world, people often use time functions on partition columns before comparing them. Starting with version 3.1, Doris can prune partitions even when those time functions are used, making it work in many more situations. In version 3.1, Doris Optimizer gains the ability to identify data traces at each node within the query plan, including properties such as unique, uniform, and equal size. By leveraging these data traces, the optimizer can perform targeted optimizations such as join elimination, aggregation elimination, and sort elimination. With this enhancement, Doris can achieve over 10 times improvement in query performance in specific scenarios. Finally, let's review the behavior changes introduced in version 3.1. In version 3.1, there are two main behavior changes. The first is related to the variant type. Queries on variant type upgraded from older version may exhibit the minor formatting differences. Extra white space or additional nesting levels may be added in result. And a new constraint, variant max subcolumns count, has been introduced. Within the same table, all variant columns must either have variant max subcolumns count set to 0 or all set to a value greater than 0. Mixing this configuration will result in an error during table creation or schema change. The second is related to permission. The permission requirement for show transaction has been changed from requiring admin priv to requiring load priv on the corresponding database. Performance for show front ends, show backends, and the node RESTful APIs have been unified. These interfaces now require select the priv on the information schema database. That's all for today's content. Thank you for all for attending the Doris webinar.